Everything we see, touch, interact with, it just seems so concrete, so real. But then you look underneath, you peek behind the curtain at the fundamental rules of the universe, quantum mechanics, and they tell a totally different story. A story where things can be in many places at once, governed by probabilities, uncertainties. It's weird. So the big question is, if the quantum world is that strange, why does our world, the everyday world, look so, so ordinary, so definite?
That is the quantum measurement problem. And it's really not just some abstract philosophical puzzle. It's the absolute core mystery of how our familiar, definite, classical reality, the one we experience, actually emerges from this deeply strange probabilistic quantum foundation that, underlies everything.
And what's really cool is that you, our listener, actually sent in an idea that I think cuts right to the heart of this. You suggested that maybe definite outcomes come from something like vibration averaging, like the mixing and then the averaging out of all the surrounding vibrational states. It feels so intuitive, doesn't it? Especially if you think about, say, classical signals, like cleaning up noisy radio reception. Averaging gets rid of the static to reveal the actual music that was already there.
That's a fantastic intuition, truly. And you're right, in classical signal processing, that's precisely what you do. You average out the noise, the random fluctuations cancel, and you reveal the signal that was already there hidden underneath. But, and this is the quantum twist, the really mind-bending part, in the quantum world, there isn't a definite state already there just waiting to be uncovered.
Exactly. That's the kicker. The system, before you look, it's in this superposition of all the possibilities at the same time. So your idea of averaging, when you apply it to quantum stuff, it can't just be revealing something that's pre-existing. It somehow has to be part of the process of creating that definite reality out of all those possibilities. That's a huge conceptual leap.
And that's really our mission for this deep dive. We want to unpack that vibration averaging idea you shared. We'll translate it into the proper language of modern quantum physics. We'll explore concepts like decoherence, einselection, quantum Darwinism, and then we'll see, okay, what challenges are still left and what are the really cutting-edge experiments trying to do right now to finally solve this mystery?
Okay, so let's lay the groundwork. The measurement problem, at its heart, it starts with these two. Well, these seem like completely contradictory rules for how quantum systems behave.
That's right. You've got what we call process one. This describes how a quantum system evolves when it's left alone, isolated. It's governed by the Schrödinger equation, and mathematically, it's beautiful. Smooth, continuous, completely deterministic. The wave function, that's the mathematical description of the system, it just evolves predictably, like clockwork, almost. If you know its state now, you know exactly what it'll be later.
And the most startling thing about this smooth linear evolution, what does it allow that just clashes with our everyday intuition?
Superposition. Because the Schrödinger equation is linear, it means a quantum particle can literally exist in multiple states at the same time. It can be, say, both spin up and spin down, or it can be in multiple places at once. It sounds crazy, but according to process one, that's perfectly fine.
Okay, but then, bam, we hit process two. Wave function collapse. And this seems to just throw process one right out the window. This rule supposedly kicks in whenever you do a measurement. And suddenly, that smooth, predictable evolution, gone. The wave function just collapses, violently, instantly, randomly.
Yeah.
That superposition reduces down to just one definite outcome. It's non-unitary, meaning it's not reversible, and it's where all the fundamental randomness in quantum mechanics comes from. The chances of getting a specific outcome are given by the Born rule.
And that's the core of the measurement problem. The theory gives us two rules, process one and process two, but no clear boundary, no definition for when you're supposed to stop using the smooth Schrödinger evolution and switch to this sudden random collapse. I mean, a measuring device, a Geiger counter, whatever, it's made of atoms too, right? It's a quantum system itself. So how can it trigger a completely different kind of evolution in the system it's measuring? It feels inconsistent.
And Schrödinger's cat is the famous thought experiment that just dramatizes this paradox perfectly. Imagine this poor cat in a box, right? With a radioactive atom, a detector, a hammer, poison, the whole setup. If the atom decays, poison is released, cat dies. If not, cat lives. But quantum mechanics says the atom goes into a superposition, decayed and not decayed. And because everything's linked, entangled, the whole system, atom, detector, cat, should end up in a superposition of dead cat and live cat.
But of course, when you open the box, you never ever see a cat that's somehow both dead and alive. You see one or the other. Definitely. So it forces the question, how does that definite outcome actually appear? what physically happens in that moment you open the box or when the detector fires.
Yeah, and traditionally, the Copenhagen interpretation sort of tried to sidestep this. It introduced this idea of a dividing line, the Heisenberg cut. Basically an arbitrary line between the quantum thing being measured and the big classical measuring device or observer. Measurement was just defined as the interaction crossing that line, and that triggered collapse. Look, pragmatically, it worked really well for physicists doing calculations for decades.
But it's not really a fundamental explanation, is it? It doesn't tell you why the cut is where it is or what physically makes the collapse happen. It's kind of like saying, okay, quantum rules apply up to here, but cross this imaginary line and suddenly, poof, a different rule takes over and we don't know why. It's unsatisfying at a deep level.
And this is precisely where your intuition, listener, about vibration averaging starts to look really powerful. Because the big breakthroughs in understanding this have come from ditching the idea of perfectly isolated quantum systems.
Exactly. Moving beyond that idealization. Real quantum systems are never perfectly isolated. They're always interacting with their environment. They're open systems.
Yeah.
And this is where your vibration averaging idea finds its rigorous physical footing through a process called decoherence.
Okay, decoherence. Tell us about that. How does this vibration averaging actually happen physically?
So imagine your quantum system. It's constantly bumping into things, interacting with its surroundings. That environment is like a huge chaotic bath, full of photons, air molecules, maybe thermal phonons in a solid, which are literally quantized vibrations. So your term vibrations is incredibly spot on here. The system is constantly being jostled and probed by its environment.
And it's not just like classical bumps and jostles, is it?
Yeah.
It's deeper than that, more quantum.
Yes, absolutely. The crucial insight isn't just classical noise, it's quantum entanglement. If your system starts in a superposition, like that particle in two places at once, its interaction with the environment creates a bigger entangled state. So the particle being in location A gets correlated with the environment being in one particular state, let's call it NVA, and the particle being in location B gets correlated with the environment being in a different state, ENVB. This is the physical mechanism. The mixing of all surrounding vibrational states you talked about is this entanglement process.
Ah, okay. So the really delicate quantum information, the thing that allows superposition, the phase relationship between here and there, it doesn't stay contained. It kind of leaks out into this huge, messy environment.
Precisely. Leaks out is a good way to put it. Or maybe spreads out into the environment's vast number of degrees of freedom. Think about trying to track the phase of a single quantum particle when it's now correlated with billions and billions of air molecules and photons, each going their own way. You effectively lose track of that phase information locally. Technically, physicists use a mathematical tool called the density matrix and perform a partial trace over the environment. This is the formal way of doing the averaging over those environmental vibrations.
But what happens when you do that? When you average over the environment, what does the system look like to us locally?
Well, for any system bigger than a few atoms, the environmental states corresponding to different system states, like NVA and ENVB, become practically orthogonal, very distinct, incredibly quickly. This causes the off-diagonal terms in the system's density matrix. Those represent the quantum coherence, the superposition to decay extremely rapidly, vanish, essentially. So the system, when you just look at it, ignoring the environment it's entangled with, appears to be in what we call a classical statistical mixture. It looks like it's either in location A or in location B with certain probabilities. It loses its ability to show interference effects. The key takeaway: entanglement with the environment makes the weird quantum superposition effects effectively disappear from our local view. It makes things look classical for all practical purposes, or FAPP, as physicists sometimes say. But notice I said, look, we need to come back to that.
Okay, right. So decoherence explains why we don't see macroscopic superpositions, why things look classical. But it doesn't necessarily explain which classical states emerge, does it? Like, why do we always see things with definite positions rather than, I don't know, superpositions of energy states or something else?
Excellent question. That's known as the preferred basis problem. And the answer comes from Wojciech-Zurich's concept of environment-induced superselection, or einselection. Decoherence isn't random. The environment doesn't just destroy any old superposition. Instead, the nature of the system-environment interaction dynamically selects a particular set of states for the system. These selected states are the ones that are most robust, most stable against further entanglement with the environment. They're called pointer states. You can think of the environment as constantly, relentlessly monitoring the system. The pointer states are the ones that remain stable and distinguishable despite this constant environmental probing. They're the fittest states in this context.
And for everyday objects, the things we see around us, position is usually the key property, right?
Right?
That's why position states are the pointer states.
Exactly. For macroscopic objects, what's the main way they interact with the environment? It's through scattering. Photons bounce off them, air molecules collide with them, and these scattering interactions are overwhelmingly sensitive to the object's position, whereas the object determines how the photons or molecules scatter. So, states of definite position are naturally selected by the environment as the stable pointer basis. Einselection explains why the classical world we see is predominantly a world of objects with definite locations, not objects in weird superpositions of, say, momentum.
Yeah.
The environment sculpts the observable reality.
Okay, so decoherence gets rid of the obvious quantum weirdness, makes things look like a classical mixture. Einselection picks out the preferred classical states, like position. That gives us a menu of definite-looking options. But how do we get from, okay, it looks classical to me, to it's objectively classical, everyone agrees on it? How does my observation line up with yours?
Now we get to quantum Darwinism, also largely developed by Zurich. This tackles the problem of objectivity. It extends the idea of the environment. The environment isn't just a passive sink that decoheres the system, it's also an active communication channel, a witness. And the key concept here is redundancy.
Redundancy, like making lots of copies.
Exactly like that. The interaction between the system and the environment doesn't just create one entanglement. It creates a massive number of redundant imprints or records of the system's pointer state, scattered across many different independent parts or fragments of the environment. Think about reading a book. Countless photons scatter off the page. Each one carries basically the same information about the letters printed there. Those scattered photons are fragments of the environment carrying redundant records of the page's state.
And we as observers, we don't need to capture all those photons, right? We just need a small fraction to read the page.
Precisely. Observers learn about the system by intercepting just a tiny fraction of these environmental records. Because the information about the system's stable pointer state, like the letters on the page or the object's position, is encoded so redundantly across the environment, any small fragment an observer happens to sample contains the complete classical information. So multiple observers sampling different tiny fragments of the environment, different sets of scattered photons, say, will all independently extract the same classical information. They'll arrive at the same conclusion about the system's state. This emergent consensus, this agreement between observers born from the redundant broadcasting of pointer state information into the environment. That is the physical origin of objectivity in quantum Darwinism. Objectivity arises because the environment acts like a massive advertising billboard, making so many copies that essentially everyone gets the same message.
That sounds like something you could potentially measure, that redundancy. It should have a specific signature.
It absolutely does. Information theory provides a very clear prediction. If you plot the amount of information about the system that's held by a fragment of the environment, as you increase the size of that fragment, you see a sharp initial rise, small fragments quickly learn something, but then it quickly levels off into a long, flat plateau, the classical plateau. This plateau means that once a fragment is just large enough to capture one redundant record, gathering more of the environment doesn't give you any new information about the system's pointer state. It just confirms what you already know. That plateau is the quantitative hallmark of objectivity emerging through redundant encoding. And it beautifully reframes measurement. It's not some instantaneous magical event. It's a continuous, messy, information spreading process. An observer is just any system, human, machine, dust particle that acquires these redundant records. No need for consciousness or anything special.
Wow. Okay, so this whole framework, decoherence, einselection, quantum Darwinism, it seems incredibly powerful. It takes us from superposition to something that looks classical, explains why certain properties like position are stable, and even explains how we all agree on those properties, achieving objectivity. So is that it? Have we solved the measurement problem? Is the mystery over?
It's incredibly powerful, yes. It explains so much about the quantum to classical transition, but no, it doesn't fully solve the original measurement problem. There's still a crucial gap. It's often called the problem of definite outcomes. Decoherence makes a quantum superposition look like and act like a classical statistical mixture for all practical purposes to any local observer. but it doesn't explain why. In any single run of an experiment, we get only one specific outcome.
This is that subtle point you mentioned earlier, the difference between something that looks like a mixture and something that truly is a mixture. The proper versus improper mixture thing.
Yes, exactly. That's the heart of the remaining issue. A proper mixture describes classical uncertainty, like I flipped a coin, covered it, and you just don't know if it's heads or tails. But it is one or the other. That's classical ignorance. Decoherence produces what's called an improper mixture. This describes the state of a subsystem, our quantum system, when it's entangled with something else, the environment. From the viewpoint of the entire combined system plus environment universe, there's still only one state, a single, gigantic, universal superposition. For Schrödinger's cat, after decoherence, from the universe's perspective, both the live cat plus correlated environment branch and the dead cat plus differently correlated environment branch still exist within this universal wave function. Decoherence explains why observers within one branch can't see or interact with the other branch they've decohered, but it doesn't actually eliminate either branch. It gives us the menu of possibilities, makes them look separate, but doesn't explain why, for us, only one item gets served in any given experiment, or which one it will be.
Okay, so if decoherence gives us the menu but doesn't explain the single choice, that sounds like where the different interpretations of quantum mechanics really come into play. They're trying to bridge that final gap.
Precisely. The major interpretations offer different ways to cross that final hurdle, to get from the decohered menu of possibilities to the single outcome we actually experience. And they paint very different pictures of what reality is fundamentally like.
Right. Let's maybe touch on the main ones. We mentioned Copenhagen earlier.
Yes, the traditional Copenhagen view essentially keeps process 2, the collapse, as fundamental. It says measurement does cause a real, physical, non-unitary collapse. Its strength, as we said, is practicality. It works for doing physics. Its challenge remains that fuzzy definition of measurement and the arbitrary Heisenberg cut. It doesn't really explain the mechanism of collapse.
Okay, then probably the most famous or infamous alternative is the many worlds interpretation, MWI.
Right. MWI takes the most radical step regarding collapse. It just throws it out completely. It says process 1, the smooth Schrödinger evolution, is all there is. The universal wave function is taken completely literally. So what happens at measurement? All possible outcomes on that decohered menu actually happen. Each occurs in its own separate parallel reality or branch or world. Decoherence is the mechanism that causes these branches to split and effectively become isolated from each other, explaining why we only perceive one outcome within our branch. Its strength is its mathematical elegance. It preserves the unitary evolution of quantum mechanics. Its big challenge for many people is, well, the sheer ontological cost, believing in the existence of countless, constantly splitting parallel universes.
Then you have things like pilot wave theory or Bohmian mechanics, a very different flavor.
Very different. Pilot wave theory says, look, particles always have definite positions, even when we're not looking. They are real particles. In addition to the wave function, there are these hidden particles. The wave function doesn't just give probabilities. It acts like a pilot wave, physically guiding the trajectories of these definite particles. So there's no collapse needed. When a measurement happens, the particle was already on one specific path, and the measurement simply reveals which path it took. Its strength is that reality is always definite and deterministic. The challenges include dealing with its inherent non-locality, faster than light influences seemingly, and making it fully compatible with relativity.
And moving away from pure interpretations, we have the objective collapse theories. These actually propose changing quantum mechanics itself.
That's the key difference, yes. Theories like GRW or Girardi-Rimini-Weber or CSL, continuous spontaneous localization, aren't just reinterpreting QM, they're proposing modifications to it. They add new, typically very small, nonlinear, and stochastic terms to the Schrödinger equation itself. These new terms cause the wave function to spontaneously collapse on its own, randomly, without needing any measurement or observer. The effect is designed to be negligible for single particles, but to amplify rapidly for large macroscopic objects, naturally leading to the definite states we see. Their strength is they provide a concrete physical mechanism for collapse within a single world picture. And crucially, because they change QM, they make specific, testable predictions that differ from standard QM. The challenge is that they are modifications, and the parameters of these new collapse terms often seem a bit arbitrary, needing experimental justification.
And lastly, maybe most philosophically different, quantum Bayesianism, cubism.
Cubism is definitely the most radical shift in perspective. It's agent-centered. It says a quantum state doesn't actually describe the physical reality of a system out there. Instead, a quantum state represents an agent's and observer's subjective degrees of belief about the likely outcomes of their future interactions with that system. So, wave function collapse isn't a physical process happening to the system. It's simply the agent updating their beliefs based on the outcome they experienced. It's like updating probabilities in classical statistics, but using the rules of quantum theory. Its strength is how it dissolves many quantum paradoxes by focusing on information and the observer's role. Its challenge is that it makes reality seem somewhat subjective, dependent on the beliefs of individual agents, which many physicists find uncomfortable.
So we have this whole landscape of ideas. For the longest time, picking one seemed like, well, like choosing your favorite flavor of philosophy. You couldn't really test them against each other. But that's changing now, isn't it? We're actually entering an era where experiments can start to put pressure on these different interpretations, maybe even rule some out.
Absolutely. It's a really exciting time for quantum foundations because it's becoming an experimental field. Take objective collapse theories. Because they predict tiny deviations from the perfect linearity of the Schrödinger equation, especially for large systems, people are looking for those deviations. There's amazing work with optomechanical systems using lasers to cool and control tiny but still macroscopic objects like mirrors on cantilevers or levitated nanoparticles. The goal is to put these increasingly massive objects into spatial superpositions and see if their evolution follows standard QM perfectly, or if there are tiny non-linearities or extra noise showing up, as predicted by collapse models. Finding any deviation would be revolutionary.
And you mentioned objective collapse also predicts a kind of universal background jiggle or heating. That sounds like another way to test them, maybe even without needing macroscopic superpositions.
Exactly. That's a different, powerful approach. The spontaneous collapse mechanism in models like GRW or CSL should be constantly giving tiny random kicks to all particles in the universe. This should lead to a very faint, universal, anomalous Brownian motion or a tiny amount of unexplained heating. So physicists are using incredibly sensitive experiments, often ones designed for other purposes like searching for dark matter or gravitational waves, to look for this faint background noise signature of spontaneous collapse.
Are these searches finding anything? Are they starting to constrain these theories?
They are putting serious pressure on them. The constraints are getting tighter and tighter, ruling out large regions of the possible parameter space for these models. For example, you mentioned the 2025 results from Xenomini, a huge dark matter detector deep underground. It's incredibly sensitive to tiny energy depositions. They used its sensitivity to search for a predicted faint X-ray emission signature from the CSL collapse model, and they set the world's best limits, ruling out the collapse rate parameter originally proposed by the theory's founders. That's a huge deal. It means the simplest, original version of CSL is now excluded by data. Proponents need to look at more complex versions or different parameter ranges. Similar constraints come from other precision experiments, the LISA Pathfinder, mission testing gravity in space, ultra-sensitive torsion balances, experiments looking at the expansion of cold atom clouds. They all chip away at the possibilities for objective collapse.
Okay, so objective collapse is being seriously tested. What about quantum Darwinism? Is that idea of redundant information and the classical plateau something we can actually observe experimentally?
Yes, definitely testable, and indeed tested. Quantum Darwinism makes that very specific prediction about information redundancy leading to the classical plateau. And there have been some really landmark experiments in recent years confirming this.
Like that 2025 study using superconducting circuits, which are basically artificial atoms used in quantum computers.
Exactly that one. They were able to carefully engineer a quantum system, a few superconducting qubits, and couple it to a controllable environment, more qubits acting as the environment. They could literally track how the information about the system's state spread into different fragments of the environment. And they directly observed the formation of those special branching states that encode the pointer information, and they measured the mutual information, clearly seeing that predicted classical plateau emerge. It was a stunning verification of the core mechanism of quantum Darwinism. Similar results are coming from other platforms, too.
It really feels like these abstract ideas from quantum foundations are colliding with cutting-edge experimental physics and information theory.
It's a true convergence. Concepts like information, redundancy, entanglement, objectivity. They're not just philosophical talking points anymore. They are becoming measurable physical quantities. We're using the tools and insights from quantum information science and quantum computing to probe the very foundations of reality itself. It's remarkable.
So let's circle back to where we started, to your incredibly insightful intuition, listener. That idea of vibration averaging. It seems like it really did capture the core physical process of decoherence, didn't it? Those vibrations are the countless degrees of freedom in the environment. Photons, phonons, particles jostling the system, and the averaging is what happens mathematically and physically when the system's quantum coherence gets hopelessly entangled and spread throughout that vast environment, making it disappear locally.
Absolutely. And your idea went even further, really. It implicitly contained the essence of inselection, too. The specific kind of vibrations, the dominant interactions with the environment, like scattering, which depends on position. Those select the stable pointer states, the menu of classical possibilities.
And finally, that mixing of all surrounding vibrational states. It's such a perfect intuitive picture of quantum Darwinism. That mixing is the environment acting as a witness, creating countless redundant copies of the system's state. And the averaging is what we observers effectively do. We just sample a tiny fraction of those environmental records. But because of the redundancy, we all get the same consistent, objective, classical picture.
It's a really powerful, intuitive framework you started with. But even with all this explanatory success, decoherence, inselection, quantum Darwinism, we have to come back to that final hurdle. This whole environmental entanglement picture explains why the world looks classical, why the menu has specific items, why we agree on the menu. But it still doesn't fundamentally solve the problem of definite outcomes.
Yeah.
It doesn't tell us why, in one specific instance, only one item from that menu is actually realized in our experience. Is it because the wave function really collapses, Copenhagen objective collapse? Is it because all items are realized in parallel worlds, MWI? Is it because there were hidden variables guiding things all along, pilot wave? Or is it about updating our beliefs, cubism? That core question remains the frontier of quantum foundations.
But what's so exciting, as we've discussed, is that this isn't just philosophy anymore. The measurement problem is actively driving some of the most precise and innovative experiments happening today, from trying to see if gravity collapses wave functions, to looking for tiny amounts of cosmic noise in dark matter detectors, to building quantum simulators to watch objectivity emerge. The final answer, whatever it is, might lie in some deeper connection between quantum mechanics, information, maybe even gravity, and these experiments are paving the way. So thinking about all this, what stands out to you the most about how our seemingly solid reality bubbles up from this weird quantum froth?